In this question, we're going to go through an example of integration by partial fractions, very common at A2 level. So to start with, I have assumed that because I have a denominator consisting of a linear term and a quadratic term, that the right-hand side can be written as a over the linear term, x plus 2, plus b over x plus 1, which is one of the factors of the quadratic term, plus c over x plus 1 squared. What I'm going to do next is get a common denominator on the right-hand side. So I have 3x over 1 plus x squared. This is my rational function. I just prefer to write it in terms of x plus 2 rather than 2 plus x. So common denominator. Well, the common denominator is going to be simply x plus 1 squared, x plus 2, which is identical to the denominator on the left-hand side. So the term with the a as the numerator has been multiplied numerator and denominator by x plus 1 squared, because if you imagine x plus 1 squared would cancel the x plus 1 squared in the bottom. So that's plus b, and then it's 1 plus x in the bottom, so it's 1 plus x, or x plus 1, x plus 2, plus c, x plus 2. Okay. So what I'm going to do now is multiply both sides by 1 plus x squared, x plus 2. I'm multiplying both sides by the denominator, which will essentially cancel it out, leaving me with 3x is equivalent to a bracket x plus 1 squared plus b bracket x plus 1, x plus 2, plus c bracket x plus 2. Because this is an identity, that's why I use the triple equal sign, I can assume that this is true for any real value of x, or any value of x. So what I'm going to do is let x equal minus 1, the intention being that I get rid of the terms which contain x plus 1. So if I let x be minus 1, on the left-hand side I have 3 times minus 1 minus 3. On the right-hand side I have minus 1 plus 1 is 0, squared times a is 0, plus 0, plus c times minus 1 plus 2. So that I have minus 3, and I may as well get rid of the identity sign now, it should be an equal sign. So minus 3 is equal to c times minus 1 plus 2, which is just 1, which means that c is minus 3. So that is one of my constants, and I can basically put that back in as necessary. What I'm going to do now is let x equal minus 2, because that will get rid of all of the terms that have minus 2 as a factor. So I have minus 6 is equal to, a times minus 2 plus 1 is minus 1, all squared, plus 0 plus 0, which means that minus 6 is equal to a times 1, which means, minus 1 squared is 1, which means a is minus 6. Finally, to get b, I can just substitute in my values for a and c, and then I should be able to find b. I can do it various ways, the easiest of which is probably to let x be 0. So let's do that now. So I'm going to let x equal 0. So that on the left I have 3 times 0 is 0. On the right I have a times x plus 1 squared. Remembering now a is minus 6. So I have minus 6 times 0 plus 1 squared plus b times 1 times 2 plus c, but we know c is minus 3 now, so I can replace that c with a minus 3. So minus 3 times, and I'm letting x be 0, so instead of x plus 2, I have 0 plus 2, which is just 2. So that means that 0 is equal to minus 6 plus 2b minus 6 solving this very simple equation, I'm going to add 6 to both sides twice, so effectively add 12 to both sides, giving me 2b, which means that b is equal to 12 divided by 2, dividing both sides by 2 to give me 6. So now I have all 3 of my constant terms. And let me just spare me while I get a new page. There we go. So we now know that a is equal to minus 3. Oh, sorry, a is equal to minus 6. B is equal to 6. And I believe C was minus 3. What was C? C was minus 3. Okay, and we substitute those back into the original expression. So we get f of x is equivalent to a over x plus 2, so minus 6 over x plus 2, plus b, which is plus 6 over x plus 1, minus 3 over x plus 1. X plus 1 squared, sorry. Okay, so that's the partial fraction expansion. What we can do now, well, that's part A for 4 marks, and then part B is to evaluate the integral, giving your answer to 3 decimal places. So what we need to do in part B is calculate the integral of f of x dx from 0 to 1. Now, my strategy for this is to call this integral I. Very creative, I for integral. Now, from our partial fractions expansion, and by the linearity of integration, because integration I can essentially separate it out when I have sums, I can say I is equal to the integral from 0 to 1 of minus 6. I'm just going to keep the order consistent with what it was. Well, actually, no, this will be easier. I'm going to say the integral of 6 over x plus 1. I can just put in the positive term first. 6 over x plus 1. Take away 6 over x plus 2. Take away 3 over x plus 1 squared. I can say that is my integral. Now, again, integration is linear, so I can basically write this as the integral from 0 to 1 of 6 over x plus 1 dx, take away the integral from 0 to 1 of 6 over x plus 2 dx, take away the integral from 0 to 1 of 3 over x plus 1 squared dx. This makes it a little bit neater. Although you don't need to do this if you don't particularly want to, but I think that's an easier way to do it. And I'm going to call each of these integrals, so I1, the middle integral, but just without the minus sign, I2. In fact, let me make this clearer. So I'm going to let I1 be integral 0 to 1 of 6 over x plus 1. I2 be the integral from 0 to 1 of 6 over x plus 2. And I3 integral 0 to 1, 3 over x plus 1 squared. There we go. Then I is simply equal to I1 take away I2 take away I3. This makes it a bit easier to see. So we'll start by working out I1. I1 is equal to the integral from 0 to 1 of 6 over x plus 1 dx, which now a lot of you will probably see straight away this is going to be like this. It's going to work out like that. If you can see that, just skip ahead. If you aren't entirely confident yet, I'm going to do this by a basic substitution. So, skip ahead if you're happy with that, but I'm just going to do a quick substitution otherwise. So, if we're not entirely happy with doing that with our log integration yet, I'm going to let u be x plus 1 so that I1 becomes the integral from 1 to 2, because when x is 0, u is 1. When x is 1, u is 2, of 6 over u. And then du by dx is just 1 because the derivative of 1 is 0, just disappears. So that means essentially the differential du is equal to the differential dx. So where I have the dx, I can replace that with a du. And then if we recall that the integral of 1 over t dt is equal to natural log of t, then I will get 6 log u from 1 to 2 as my integral, as my my definite integral. So I get I1 is 6 log 2 take away 6 log 1. I'm just substituting in 2 and then substituting in 1 and finding the difference. And log 1, remember, the natural log of 1 is the number that I have to raise e2 to get 1, which is just 0. So I have 6 log 2. Very straightforward. So I1 should be 6 times the natural log of 2. To find I2, so just remember for my definition, I2 is integral 0 to 1, 6 over x plus 2. So this is going to work out very similar again. If you are happy with the fact that this is going to be like this, if you're happy with that, if you can just see the result of the integration, just skip ahead. Otherwise, again, I'm going to do a simple substitution and make use of the natural log integral. So I'm going to let u be x plus 2, so that once again I have I2 being the integral from, so 2 to 3, 6 over u, and then again du is equal to dx because it's simply linear. Du by dx is 1, therefore du is dx. So I2 is equal to, this time, 6 log u, 2 to 3. So I have 6 log 3 take away 6 log 2 for my I2. And then finally for I3, this one won't require the log integral. I3 is equal to the integral from 0 to 1 of 3 over x plus 1 squared. And once again, a lot of you will probably just see that this is going to be minus 3 x plus 1 to the minus 1 from 0 to 1. A lot of you will probably just see that. But again, I'm going to do a simple substitution just if we're not entirely sure yet. So I'm going to let u be x plus 1. Then my integral becomes the integral from 0 plus 1 is 1, 1 plus 1 is 2, obviously. So I have 3 over u squared, and again, du is equal to dx, so I have du. So I have, again, remembering my power rule, this is really the integral from 1 to 2 of 3u to the minus 2 du. We add 1 to the power, divide by the new power, which is minus 1. So we are left with minus 3 u to the minus 1. I always check, does this differentiate to what I want and what I have? Does this differentiate back to my integrand in my head? It does. Minus 1, 3, minus 2. And those are my limits. So I have I3 equal to, now personally the easiest thing for me to do is to take out the minus 3 as a factor. So I have minus 3, 2 to the minus 1, take away 1 to the minus 1, which implies I3 is equal to minus 3, 1 over 2, take away 1 over 1, which is 1, which is minus 3 times 1 half take away 1, which is minus a half, and that's a really dodgy 2. Minus 3 times minus a half is just 3 over 2, 1.5, which is my result for I3. And going back to the way I defined it, I is equal to I1 take away I2 take away I3. So I is equal to 6 log 2. Take away I2, which is just 6 log 3 take away 6 log 2. Take away I3, which is 1.5. And that leaves me with 6 log 2 take away 6 log 3 minus 1 essentially times minus 6 log 2 is plus 6 log 2. And then I have a minus 3 over 2 on the end. 6 log 2 plus 6 log 2 is 12 log 2. So I have 12 log 2, take away 6 log 3, take away 1.5. Now, they're asking for the answer to, I believe, 2 decimal places, or 3 decimal places. So I think the reason they're asking for 3 decimal places is because they want you to manipulate it down to this stage and then put it into your calculator. They don't want you using, they don't want you rounding I1 and I2 and I3. They want you rounding at the end. So, we could very easily manipulate these logs down, but the easiest thing to do at this stage of the modern calculator is just to put it in. So we have 12 log 2, take away 6 log 3, take away, again, 3 over 2 is 1.5, equals 0.2261, or to 3 decimal places, 0.226, which would be our final answer.